The target today is to look at the inverter technologies and the wide-bandgap devices that we have. Let's start. We just have a small outlines, but it seems small. And we have an introduction, motivation, and later we discuss about the inverter technologies in different areas, and then at the end, and the conclusion. Okay, introductions. You know that in the passenger cars, we have many demands recently in the market. Especially, we have many players now in the market, and they push us to have a better, for example, power and torque. We have a higher efficiency, lower cost, higher power density, more robust solutions, reliable solutions, and even more sustainable solutions. And then what we should do? We are first look at the market from both perspectives, what is available and what is coming in the future. And also we look at all the researchers in all areas and try to understand what is next. And we also need to evaluate that one. Then based off that one, then we make our roadmap for our technologies that we are going to have in the future. Okay, we can say that this. Okay, we have had a lot of slides yesterday about that one. This graph, it is maybe a little old, but since we are going to use these wide-bandgap devices in the inverter, which is a part of the EDU that we call that one electric drive unit, this is very critical that we understand the effect of the wide-bandgap devices due to all its benefits to our inverter. And this is the reason that we are going to have to show this presentation, going to focus on it. As we discussed, there are many KPIs that should be optimized for the inverter. You will see some of them here: cost, for example, sustainability, reliability, customers, efficiency. Some of them are legal. When they are legal, it is legal. No deviation we can have. And some of them is still, we can play with that one, customer experience and efficiency. When we talk about for example, customer experience is a little, I can say, vague word. We talk a little about the range, performance, how it works. And also we know that there are different topologies, different architecture, many components available in inverter, and like, for example, power module, DC link cap, filters, and everything that we have. And then this is really challenging to optimize all these KPIs at the same time. Sometimes it's impossible. We need to sacrifice some of them, but it is really difficult. I can say, fortunately or unfortunately, introduction of some new technologies affect the other technologies as well that we have in inverter. For example, when we bring the wide-bandgap devices, it's not only to introduction, okay, we have a wide-bandgap devices, let's start. They are affecting all these components that we have discussed because they have a mutual effect on each other. And I think you know better than me. In this presentation, we try to focus a little, not only on the wide-bandgap, but also more on the other technologies that can be affected by introduction of the wide-bandgap. Because I have seen that we have had a lot of introductions for the wide-bandgap devices yesterday, and I can say we have a little here, but we try to go to I remove some of the slides to make that one less in that regard. Okay, let's see that in which area we are going to investigate or to show the inverter technology and how the wide-bandgap devices can affect that one and how to optimize the system that it works with the wide-bandgap devices. And if you look at that one, I think technologies that we have in inverter is not limited to this, but we have in two main categories is the system, and the second one is the components. In the system, wide bandgap devices could affect the architecture, topologies, control and functional safety logic that we have, and much more that we have listed here. But also on a component level, okay, power module is clear. It can be affected by these wide bandgap devices. But it's not only power module. DC link cap can be affected, gate driver can be affected, EMC filter can be affected, sensor actuator that we have inside the inverter can be affected only by changing this from, for example, IGBT to the silicon carbide or the GaN. Let's go a little further. First, look at that one from architecture. Which architecture that we see in right now and in the future? We see most of the OEMs started to go to higher voltage, not only for 400 voltage, 800 volt, and they're even higher. And we have seen the current, it was before we have started, I can say 150 amp RMS. I can say maybe a couple of years ago, 400 amp RMS, and now the request is for 700 amp RMS. And they think that if you have, depends on the voltage of the system, it could be if maybe we try to, one of the reasons that we go to the higher voltage, that we have a less current here, but still they are high demand on the 800 volt system for the current. And this is one of the limitations that we have that we are going to use. And also this will affect the devices that you can use. Cooling, that can be affected by wide gap. We need the active cooling for the power module. That all of them we have had even from the IGBTs. But when we go, if you're going to use really benefit from the wide bandgap, we need a little more active cooling for the system. It means like we need to have even active cooling for the active and passive components that they have. We will see that one, that is those components like a DC link cap and EMC filter. Without them, they are not so much effective without active cooling. And water cooling, this is a technology that we have had before water cooling, or like say G64 cooling. Then recently, we have both water and the oil cooling. And we have also see that the new technology comes for the direct chip cooling that we are still haven't used that one, but this is a new technology that should be used. And also for the packaging, okay, we know that one of the reasons that we are going to silicon carbide is the smaller components can make a smaller power module. We can have a higher power density, but maybe it is, we think that in the packaging we can have a higher power density, and also we have to, when we use the wide bandgap devices, to make that one more integration between power module and DC link cap, and even the EMC filter. Otherwise, we cannot we cannot benefit fully from the inverter efficiency or EMI problem that we have. I think this is something that in architecture can be affected. As I said, this is not limited to that one, but we have much more. But I just limited that one here. And also topologies. When we talk about the inverter technology in the topologies, we think about the different topology of the hardware, like, for example, 2-level to the multi-level, depending on which type. And also we have a lot of wideband. If you're going to use the wide bandgap devices, they make some limitations for us, depending on which wide-bandgap devices that we are using. But we see that if you're going to use the multi-level and we benefit from that one, it is better that we go to the wide-bandgap devices as well. And also beneficial for the high system efficiency improvement. We see that the multi-level, we can benefit for the system efficiency, but it's not only related to the wide bandgap devices, it is related to the 2-level, but Wide-Bandgap device, it doesn't let us to go to select any topologies that we like. We have to combine the wide-bandgap and, for example, other devices. And the soft switching as well, and either in two-level or multi-level. I can say that they have both technology are really costly because we have more devices here, and we have also more devices here. And then since they are most costly for the wide-bandgap devices, we see that is a little challenging for us if you're going to use that one. And the only solution that we can see, we need to reduce the operational cost by increasing the system efficiency. What does it mean? It means that, okay, I increase the efficiency, then I reduce the, for example, energy that I losses, then I can use less number of the cells, for example, in the battery, and then I can benefit from that one, because then I can save the cost and use that cost for these wide-bandgap devices. This is, for example, we call it an operational cost. At least we call that one. And also inverter technology, we have, I like to, okay, I was started a little late, I think. Okay, but inverter technology also we have to affect the control and fuzzer logics, and also wide-bandgap devices. We know that they are very sensitive, fast device, and they have a different wide-bandgap devices provider, and they are expensive. And due to that one, when we talk about the control and fuzzer logics, we need to have different topologies in this method, and also different switching methodologies, different topologies and different switching methodologies. And one of the solutions that we can solve this, all this, we can benefit from the wide-bandgap devices, is that we move from the this ordinary solution that we have had to go to the little more system on a chip, or maybe FPGA solution like this one that you can see. I can say system and FPGA and, for example, normal drivers, or even we put more control system inside the FPGA instead of putting a lot of load on the CPU. And also on the power module level that we have discussed a lot, we know that the technology is going to go to from half bridge to the full bridge to the embedded technology. And ordinary power module is going to become more integrated and intelligent power module that we will discuss about that one in the panel a little. And we see that the cooling, we have seen before we have had only single side cooling. We see that this is a technology that will come. It's very challenging from mechanical perspective and packaging, but we have used that one from 9 years ago, 8 years ago, double side cooling, and it works. Why this is necessary? SiC price is very high. If I can save one chip, I put $6 in my pocket for each switch, at least. And also we have seen that pin fins, this is, they are started to customize the pin fins. Tesla, for example, started 2018, 2017, 18. And also team material is going to switch to the soldering sintering and the soldering sintering combination in double side cooling. And also base plate cooling we have had before. This is going to be direct chip cooling. This is a new technology, but it has its own some limitations also due to the stresses that we have. And also we see the substrate material change, and we are following that one. We ask our suppliers, or we are going to use that one. And this is a ceramic before, and from different ceramic material to non-ceramic in embedded power module, and also IMS. An electrical carrier also, it was before DCB and AMB that is going to new technology with more, I can say, PCB-based. And terminals also, we know that it's very important to have an overlap terminal to minimize the parasitics, but I can say the parasitics we are going to use mostly. Right now we are using the laser welding, but in the future we are going to do the ultrasolid welding and we have seen the better results. We have tested that one. And also, regarding the die, I think you know that we have switched to the silicon carbide, and maybe in the future we combine silicon carbide and IGBTs, like what Tesla has reported recently. And also for the GaN, also D mode, E mode, and the D3 mode is our technology that we can see in the future. And also for the die attachment from the old solutions, we try to go to the, for example, soldering to sintering and even nano-copper that is recently introduced, but is still in the advanced engineering level, I can say. And also topside die contact could be wire bonding, could be copper clips that they have explained yesterday, and it could be a spacer that they have explained yesterday. But as I said, even for the, there are more methods also for here. Look at the DC link cap. DC link cap, we have a, if you're going to benefit really from the wide bandgap devices, DC link cap is one of the crucial components that we have, one of the critical components that we have. Those technologies that we can see is instead of using single DC link cap, they have a possibility to have a distributed DC link cap to decrease the parasitics. And also we have seen that they try to minimize the internal parasitic inductance and resistance. This is, we know a little about that one, and then we have some expectations, some requirements that we push the supplier to provide. And also we try to minimize the power module connection parasitic inductance. For example, this link cap is completely unacceptable, rejected, but I couldn't put, I'll say, all solutions. I can say this has a lot of parasitics, both internally and externally, to connect to the power module. And we try to have a more integration of this link inside this link cap, like EMC passive components, like a Tesla, plus temperature sensor inside to detect the temperature and have actively control the temperature of that one, like Hyundai, and also we have a DC current sensor inside. We need to have that one. It is possible to integrate that one. This is a technology that we have seen in all the OEMs that is coming. And that is especially for the EMC passive, since we are going to use the wide bandgap devices. If we don't make that one very close to the terminals that we have here, this is actually all the bus bars could be antenna and send the noise outside. And I think before it was a cooling through the housing, polymer housing, but we try to have an active cooling plate on a capacitor to have a connected somehow to the internal structure of that one to have a very, very efficient cooling for the critical points of the DC link cap. Material, before it was 105 degrees, now we have a 135 degrees. We need to replace film. We go from the film capacitor to the polymer capacitor, like that is very, very, we have tested that one, that is very, very good and promising. Microfilm to the nanofilm metallizations. Before we have a microfilm, now recently we have a nanofilm plus the dendrites that they have a much better performance, and both from our parasitics and also from losses. It's a part of the parasitics. And also, instead, this is very heavy component inside the inverter. We have seen that some suppliers use the aluminum copper coated based DC link cap. And we have requested to test one of them to see how it works. We haven't tested yet. And also for the gate driver, we see that if you're going to use the wide bandgap driver, they are very important to have a right gate driver. Yes, I see. Okay, let's do have a very fast. I can say the gate driver should have many facilities to cover the wide bandgap because they are very sensitive component. But the most important things is that we need to have a multi-level or active current source driver or even discrete PWM pulses with a lot of configurable parameters because we have a different chip supplier that they have a different characteristics, and this is very critical to have configurations. And also, we like to have extra facilities also inside, like ADCs, temperature sensors, and everything that it can support us, even the control port of the switching power supply to have more and more integrations. And for the maybe multi-level, as we discussed, we need to have a FPGA with a simple driver to drive the multi-levels. I have 3 slides, I think. I hope I can finish that one. And from this EMC filter, also we have a lot of challenging. And because this is a wide-bandgap devices, we are going to use benefit wide-bandgap devices with a higher DVDT, have a more ringing, for example, more EMI problem. And then we have start to have a problem for the filter, EMC filter. And we are using both EMC filter in input and output, and for the removing the common mode current or the differential mode current. We try to encapsulate EMI filter in the EMI place, like inside the DC link cap. We try to have a more stage of the filter, high performance core material like a non-crystalline. And with all these common mode and differential mode should be active cooling with a high value of the, and also capacitor technology is very important, that we need to have a very low parasitics capacitors, and also with a very high, with both values low and high, that we can have a benefit from that one. We have also for sensor, let me to SCAPE, and we go to the conclusion about this is also important. I can say that using the wide-bandgap devices is a part of technology roadmap that we have, and everybody is using. We are only, we have to reuse that one. But there are a lot of challenges to fulfill the customer and legal demands. And also using wideband devices can affect technologies, not technology that we have. Many technologies in the DC link cap, EMC filter, on a bus bars, on a gate driver, on a topology that we are selecting, on the architecture that we have, all of them can be affected. And also selection of the right combination of this technology that we can really benefit from wide-bandgap devices is very, very critical. Right now, I can say we have seen many people, they are using these components, this type of wideband, but since they haven't optimized the whole system, they cannot see the real benefits of that one. And we have seen when we go to the start, step by step, make that one better and more flexible, reliable, for example, for the gate driver. And then we have seen the more and more benefits of that one. This is very, very crucial, I can say. And maybe the last statement, I think let's work together to make the wide-bandgap devices as a better technology to our world. This is not only device. This is a whole application of that one should be, in all aspects, should be updated. Otherwise, we cannot benefit from that one. Thank you very much.
Thank you very much. Unfortunately, we are running already late, so we skip the questions and move it to one question. Okay. But it's not a short question.
You were showing an image of a GAN, of a GAN converter in your system. Can you say anything about environmental compatibility of these technology? I mean, combination of high humidity, high voltage.
Yeah, that's true. Actually, we will discuss about that one. Let's discuss about that one in the panel. I have a specific item for that one inside the panel presentation for this GAN and how we can apply it. Thank you for your questions. Let's do little, yeah. Any more questions?
No, we have to move on.
Thank you, thank you, thank you. Thank you.
So the next presentation is from Johan Helsing from HART. adoption of silicon carbide technology in an aeronautical application. Please go ahead.
Thank you. Good morning. I can assure you that none of my slides have been seen before because I will not come very much into the inverter technology, but bear with me. In the end, it will come down to at least one final slide about our requirements on inverters on a very general level. But I will take you through maybe what I experienced in my first year in the aerospace. My background has been 25 years in the automotive industry, developing electric drive lines, motors, and power electronics, and the installation of these. And it's a little bit of different thinking, so that's what I will go through with you. Main focus here is on the aeronautical technology. Talking about the date of today, actually later this afternoon, you can look on LinkedIn, and so there will be some press releases from our company about our strategy. So I could not show it because it will be this afternoon released and not in the morning. We are a Swedish company located in Gothenburg, and we design and build electric aircrafts, including the propulsion system. I'm responsible for the electric motor and the electric propulsion system, we could say, and also involved in the high voltage system and the EMC. So pretty wide area, that's me. We are a quite small propulsion team. But talking about why we do this, an electric aircraft for a 30-seater, we are focusing the regional area here. There are other areas where electric aviation is taking place. The urban air mobility is many active projects around the world. It's not a market which is mature. We'll see how it goes, but there it's quite a lot of things ongoing. We are not there. A bit smaller aircrafts with 7 up to 18 passengers is an existing market, but not maybe with so much potential to expand. But for sure, into electric, it's a little bit easier. We focus on the regional area here, which is an existing market, which has been bigger and has decreased. And we are here to unlock a bit of the demand by going electric, to start using more local airports. And one of the things is maybe we are a commuter into bigger airport hubs, and we think that is interesting to do emission-free and noise, with less noise. And the 100-plus passenger market is something which is more than 10 years away. So there we also are a bit more passive. Of course, the challenges is cost, how we and climate impact. That's our main drivers. And from a market perspective, we are looking into growing in major hubs and connect into those. And there are a lot of existing regional airports which are underused. So this is and of course there are some existing connections to the island of Gotland or something like that, where aviation would be a nice thing. So we are regenerating regional flying, and this is the specs for the aircraft. We start with 30 passengers, and the all-electric range is 200 kilometers, but it's a hybrid system, so 400 to 800 kilometers is the maximum range, depending a little bit on how many passengers. We should be able to recharge in 30 minutes, and the runway should not be more than 1,100 meters. That is not very long, but not extremely short either, but to cover the regional airports. And in 2028, we aim to reach type certificate for the aircraft. We will later this year show this demonstrator, which is not intended to fly. It's for charging and for taxi. So it will have lower power propulsion. And it's built all in carbon fiber, and it's this is pictures from just a couple of weeks ago in Göteborg. The performance will improve over time. We start with the best batteries we find now, of course, with a good safety level and everything. I think it's pretty clear that it's similar to what the best electric vehicles can reach. But we also have the batteries are not very hard built into the system, so it will be easy to replace. The aircraft are designed for 30 years of life, and the batteries will not live that long for our harsh use. So we also know that we in 5 years and in 10 years can offer more full electric range, 300, 400 kilometers. The left picture is showing a bit that much of the energy is taken during climb up to the altitude. And when you are up there cruising, you don't need that much extra. I mean, you don't need twice the amount of energy to go 400 kilometer all electric. That's clear. So, okay, I was expecting some slideshow here, but okay, from the top here. What do I, as a designer of electric propulsion, need to know? Pretty much, what is the torque of the shaft? We use propellers. It's the most energy efficient propulsor, and the thrust which we need to propel the aircraft is related to shaft torque. So the picture up to the right is describing like a fan curve, nothing very fancy, so to say, but you can see that it's the highest thrust at the highest speeds for the propeller, which means also it's the highest torque at the highest speed. So we have no reason to go into field weakening for the electric motor and those issues related to that. So it's constant torque up to maximum speed. That's what we need from the motor. Actually, at low speed, we don't need high torque at all. So that's our only load. In that sense, relatively easy. And then about energy efficiency, I said it is efficient, but it is efficient. The efficiency of the propeller is related to what is the wind speed towards the aircraft. And as that varies from start up to full speed, we need to have a pitch angle of the propeller which can be variated so that we can reach best efficiency regardless of airspeed. And the maximum efficiency of the propeller is around 85%. So it's not that bad at all. Talking about efficiency, I don't think I write the number in. For the motor and the inverter together, we require at least 96% efficient. Also, lacking the slideshow, the thing is I wanted to start up to the right here. And this is about the requirements which we have to live in. It's a quite regulated market. And I cannot, this is too close for me with the screen for my, my old eyes. So I have to look up here. Up to the right there, what is happening in the European and US aviation safety agencies is that they are focusing the safety assessments first about how it's the power loss rates, and LOPC is loss of power control, means that lack of the control of the propulsion system means that we lack control of the propulsion power. And that's down to the left there, I will come to there. And the GA level 1 and 2 are smaller aircrafts. So for the size of aircrafts we are developing, the regulations are not really in place. Maybe the general safety regulations, but not the means of compliance. What do you actually have to fulfill to be seen as safe? So we are kind of shaping the regulations in parallel to our technical development. But I put this up to the right just to show what the safety agencies are focusing. How you do the single fault tolerance. We have to, it's a comment that we have to design for a single fault. It's not, of course it should happen as seldom as possible, but it will happen. So what will happen then? And we should hopefully avoid double faults. But it's really designed for single fault that is really central for aviation, I would say. Also, as we are an aircraft with wings, it's bad to lose the propulsion power, but it's even worse to lose the wings, so to say. So the last thing on the blue there, containment, that's really crucial. I don't think it's very worrisome that something gets loose from if we lose the inverter from the fixations or the motor overspeeds or something like that. Quite unlikely, but that is the number one critical thing, actually. And then, of course, we should have the propulsion power as well. But ratings, safety assessments, fire protections, vibrations, up to the yellow there. There are some of the top levels which they want the electric engine to first go through. And some of the control system architecture, and so they have not even started discussing this. It's quite clear that the control unit, the intelligence, so to say, the control board, the sensors, the power modules, the windings of the motor, those will have to be single fault tolerant, means redundant systems. And down to the left there is, MCP is maximum continuous, and maximum takeoff, that's short time. It's kind of self-explanatory. As you see, duration unlimited, duration 3 minutes. So the two first lines there, that's the normal operation. So 80% power of the maximum continuous and 100% then during a few minutes. That's a typical operation we have to live with. And the E in the next two lines is emergency. So emergency short duration and emergency continuous duration. And that's what is kind of crucial for the design of the propulsion system, that we will have to, it's still draft, but so you understand the thinking here. During 2 minutes, we should, in any single fault condition, we should be able to deliver 80% power. And continuously, maybe 50%. So that dictates a bit about how we develop the technology. And what we are doing now is looking into, I would say we are focusing the direct drive motor here. We could do, some suppliers would like to propose a gearbox design, what you are used to more from the electric vehicles, with a 10,000-ish electric motor and a gearbox to the propeller, which needs some 1,500 RPM. Gearbox is a source of failure, not very likely, but the thing is, one single failure would kill the whole engine. And if we do a direct drive, we still have bearings, but that's the only mechanical part left. So we are looking into direct drive and do a quite modular stator design where single faults remain in one part of the engine. So just to describe it principally, if we have an inverter with 200 kilowatt feeding a three-phase motor, that's what we are used to discuss in these sessions. But if we go to twice the power, we're not requesting a 400 kilowatt inverter. We are requesting the same inverter, but a motor with dual windings. And that means that we have one winding working if we have one failure of one inverter. And the thing, if we go to even higher power, we will go even above 800 kilowatt, a bit higher. But the principle is here that the inverter power is not that super high, and also the inverter reliability is kind of, I don't know if I should use the word limited, but so now coming here to the kind of conclusion. Loss of all motor power may occur. That means we should prove that it doesn't happen more often. than once in 100 million flight hours. So that's the level of one motor plus the inverters together. And by doing the design with maybe 4 inverters feeding one motor with 4 individual windings, that means that we can have one of these, a single failure, may occur in 1,000 to 10,000 hours, somewhere there. We are not done the safety assessment ready yet, but we are somewhere there. And that means we are on the same level as automotive, I would say. So from an inverter perspective, that's kind of my message here. It's fairly standard. Took me a long time to come there. And also power level, I don't expect us to go higher than 400 kilowatt because we have this need of doing redundant systems anyway. 800 volt we have chosen as a DC voltage right now, and the high efficiency is obvious, and I put it above the reliability. No, sorry, but I didn't even put weight here. Weight is important, always discussed in aerospace. But as we have batteries, which have such a high weight, much higher than the propulsion system, efficiency comes up very high. And weight is good to have low, but it's more important with efficiency. Status monitoring of the inverter is interesting. If it's possible to predict that it's likely a fault will come, that will of course be very interesting for the aerospace industry, because if we can have a planned maintenance, so much better for the operators than a change of a faulty component. Even if the fault is kind of minor, if we lose just one inverter, it still takes time to change. So very, very good if we have a good monitoring status. Reliability is still high, yes, but kind of, I would say, similar as in the automotive industry. Redundancy in each inverter is not required. It's kind of built into the motor design as I described, but maybe the rotor position sensing, that will have to be redundant. And because of that, I see sensorless motor control as quite interesting to, as the ordinary control or the backup, but to have like a redundancy there. So this is what I wanted to go through. There is, of course, some more power electronics in the aircraft than the propulsion system, but this is the main part. And I will also mention, I will unfortunately have to leave it in the next break for my train back to Gothenburg. So, but you can catch me in the break if you like. So thank you for listening, and thank you for inviting me to this days.
Yeah, thank you very much. Mirtek wants me to allow one question.
Yeah, the question was about multiphase. It's to rely to this requirements on single control failure. It's kind of better to have 2 3-phase systems, 2 3-phase windings in the motor with separate inverters, totally separately controlled, instead of a 6-phase motor, if you see what I mean, because then it would be one controller. But it is multi-phase could be good for efficiency, perhaps, or EMI. But it's otherwise it's an ordinary 3-phase, I would say. Which way?
2 engine both sides, and then if one of the phase still this works. You mean that
Yeah, we have two electric motors, yes, but even one failing is very severe. So that is like the once in 100 million flight hours. So it should never happen in principle that one motor fails, but a part of one motor. And that's my message here, that we will design motors different than what you're used to, and which also have an impact on the inverter design, because the inverter design will be more standard.
Yeah, thanks. Okay, we move to the next presentation. It's from Scania. Ninos Poli will do the talk, and the use of wide bandgap semiconductors in Scania's products.
I have a timer with me, so let's see if that helps keeping the track of time. Okay, first of all, I would like to thank the SCAPE conference and Metec for inviting Scania and me to present at this event. I will talk about the use of silicon carbide. I wrote Wide-Bandgap, but we use silicon carbide in our products, and I will mention a couple of them here. So as I said, I come from Scania. I've been working there for almost 15 years now, mainly with e-mobility components. My current role is something that we call technology leader. And what we do is we have different themes. I'm responsible for the theme of vehicle propulsion, so it covers the combustion engine and the electric drivetrain and everything in between there. So we set up different targets in our research roadmap, and then we make sure that these targets are fulfilled by allocating resources and make sure that activities are ongoing. So in this context, we have electric drive inverter electric machines that is relevant for today. Basically, in short, you can say that we try to figure out what kind of research we should perform within this field and when in time. As you might know by now, Scania is part of the Traton Group, together with MAN, Navistar, and Volkswagen. So that means if we develop a component, it has to be compatible with the rest of the brands in the same group. So we have a modular system that I will come to soon. But first, oops, it's sensitive. Yeah, so what's the purpose of Scania? So Scania's purpose is to drive the shift towards a sustainable transport system, creating a world of mobility that's better for business, society, and environment. But also to make money, of course. I mean, we need to make profit, otherwise we cannot do research, we cannot continue living on. So that destroyed the whole joke. So Scania has a long history. I will not go into all the milestones, I will mention a couple of them. It was founded in 1891. We were producing bicycles and railroad carriages. So it's pretty funny that we start with bicycles and then 130, 40 years later we have a battery factory. But a couple of milestones. Our first truck was built 120 years ago. Then in 2000, we built our 1 millionth truck. Our first fully electric truck in 2020. And then we built our battery assembly factory last year. So we purchased cells from Northvolt, we assemble them in modules and then into packs. And then I can mention also that we demonstrated the charging with a megawatt charging standard last year together with ABB. And then we have some couple of other milestones in the future that we hope to achieve. I will get back to some of those. So Scania in brief, we have approximately 58,000 employees worldwide. We have several production plants all over the world, for example, in Brazil. But the main production plant and R&D is located in Södertälje, south of Stockholm. And I can mention that last year we had a record year. We sold up to 96,000 units. And out of those 96,000, 91 were trucks, 10,000 more than the year before, 5,000 buses and 13,000 engines to marine and gensets and so on. So it was a good year last year. Here is the market share for in Europe for Scania and different truck companies. And I have to be humble here and give credit to Volvo. They passed us in market share in Europe. We've been close to each other along the way, but they passed us. Somehow they managed the semiconductor shortage crisis better than us in 2022. But yeah, we have the ambition to catch up soon. However, I can brag with winning the Green Truck Award of the Year for the 6th time. So that we are proud of. So in addition to the legal requirements when it comes to CO2 emissions, we have committed to other requirements as well, the so-called science-based targets, which states that we have to reduce the CO2 emissions by 50% from our operations and 20% from our rolling fleet. So this is, we are pretty close to reach this one. I think we're up to 44% by date, and then we're on the way on this other topic. And to help us achieve these targets, to reduce CO2, which is the main purpose now, is to electrify our product portfolio. So the future is electric, which we can all agree on, and that's also the vision of Scania. So we have a clear statement from our management saying that the days of the fossil-fueled vehicles are numbered, and shifting towards electrical vehicles is vital, and so on. So we expect a drastic ramp up in our sales of electric vehicles. So our ambition is that by 2030, half of our vehicles should be electrified. So it's a bold statement. So if you think about it, we sold 96,000 trucks last year. So by 2030, we're aiming to sell half of those, so 50,000, 45,000 electrified trucks. So it's a bold statement and ambitious goal, but we hope to achieve that. And yeah, to help us on that journey is our so-called modular system. It's one of Scania's foundations and one of our winning concepts. So by combining a couple of components together, we can create many varieties of trucks and buses. So for example, you can choose different sizes on electric machines together with batteries, charging inlets, and so on. And then you can create your tailored solution, truck or bus for different applications and so on. Here you see an overview of our electrified product portfolio. I can mention that we have since several years now, maybe 10 years almost, hybrid electric vehicle buses and trucks. And then we launched the new plug-in hybrid trucks and buses, but also rather recently the electric truck for urban and regional transport. I will show some pictures soon. BEV bus as well for inner city. But our, let's say, the flagship, the thing that will help us earn this money that I was talking about, it's the long haulage. So BEV full electric long haulage trucks will be coming soon. And below here are some of our demonstrator research projects that we have been working on together with partners. So this is some pictures of our BEV truck for urban and regional transport. And you see here in the gold where we have our electric motor and so on. We have a permanent magnet synchronous electric motor with oil spray cooling, a power level 230 kilowatts or 450 kilowatts. So we have different performance step, which I will show soon. We have a dual inverter with two separate outputs to control the electric machine. When it comes to battery packs, the customer can choose between different number of packs, as I said, to have different amount of installed capacity. Now for the urban and regional, you can have different amount. Then you have a CCS charging inlet. For the urban, you have only 130 kilowatts charging power, whereas in the regional, you have 375. But still, it takes up to 90 minutes to charge the truck fully. So it's a lot of time. Imagine if you reach a charging station depot and there are 5 trucks in front of you with everybody wants to charge for hours. It's not feasible like that. So we need to be able to charge faster. And that's where this megawatt charging standard comes in, to charge at higher power levels and maybe higher voltages as well. So we are working on that topic separately. Here are some more pictures of the electrical components. And here we have an overview of the main components in our BEV trucks. We have, for example, a climate system, compressed air system. Yeah, so all the components that are being driven by belts and so on by the combustion engine have to be electrified now. But for today, we will focus on the powertrain, as you can see here. We have different variants, performance steps of the electric machine and the inverter that you can combine together to reach different performance levels and power levels. So we'll go through them now. We have our current inverter, which is based on silicon IGBTs. This one is produced by our Emotion guys here. It's a dual inverter with 2 separate outputs to control 2 electric machines. And we have a single e-machine that we will call here, in this case, single. That e-machine can be connected in series with another single e-machine, which you can control separately. So let's call that a dual e-machine with 2 singles. And then you can think, if you connect these 2 in parallel instead, and have longer width, depth of the electric machine, so that you achieve a big single e-machine with twice the power at least. So 1 single, 2 single in series, a dual, or 1 big single with 2 in parallel, all driven by this inverter here. So here is a couple of variants. You have the single e-machine together with the gearbox with these kind of power levels. Then you have the dual, so it's 2 separate electric machines connected with the gearbox. The big single e-machine, and then we have the biggest performance step that we call, I call it here, big single plus dual. So the big performance step here is 3 e-machines, 1 big single and 2 dual, so 2 separate that you can control separately. And that way you can achieve torque-free interruption when shifting gears. So it's like power shifting. And the power level is, as I mentioned here, 430 kilowatts. So that's in our current products now. For the next generation, we have an inverter that I have put there on the table there. Behind, you see there. So this one is based on silicon carbide MOSFETs, and this one is placed on top of the electric machine. Before it was separate. This one is placed on top and connected via bus bars to the electric machine. This one comes also at different performance steps, both the inverter and the electric machine. Let's see here. And it's called, it's central drive electric machine with a couple of gears, but there's a configuration where you can mount this one in the axle, so it's like an e-axle configuration. So this one comes at different performance steps and different configurations as well. So for this generation, we have developed the housing, the cooling, the lubrication and the gearbox. But it's still oil-cooled electric machine. And as I said, it comes at different performance steps and different power levels. So we have compared now the 2 different generations, the coming generation, the ongoing one, the current. The efficiency for the one with the silicon carbide is approximately 1% higher than the one with silicon IGBTs. And you might think 1% is not much, but every percent counts, especially if you have like a long haulage application. And we have estimated that 1% is approximately cost 1,000 euros for the customer. So we need to take into consideration every percent. And also, you could have less batteries for the same amount of range. But it's not only the efficiency in this case. I mean, the size, you see the component there, the size, the weight, it's a bit smaller than the current generation. Okay, so far, historically, when we develop an inverter, we assume the so-called black box point of view. So we specify the input, output, current, voltages, temperatures, the form factor, the weight, the efficiency, and so on. Then we hand it over to the supplier and say, okay, fulfill these requirements. Which they do sometimes, many times, but we want to move away from that approach. We want to get our hands dirty. We want to be involved in the project from an early stage so that we learn and perhaps in the future build our own inverters and electric machines in the future. So that's something that we look into, the possibility to produce stuff ourselves. So that's why we have some research activities ongoing. We have built our couple of prototype inverters. I will show the first one here. This one is based on silicon carbide MOSFETs. It's on a PCB level, so it's a bit simpler. We have performed functional testing in lab in a back-to-back rig at Scania at lower voltage levels and power levels. And then we have produced another generation, also based on silicon carbide. But here we have a housing that we developed at Scania with cooling. So this one is much more robust, so we can drive it at higher power levels, at higher voltages, but also it's been tested in vehicles very recently. So it's very exciting now that we are developing inverters and testing those in vehicles and in lab. And also we have tried some of our own software to control the electric machine via these inverters. This inverter, since we design it ourselves, the software and the hardware, we can control, we have much more flexibility, so we can control different electric machines with or without permanent magnet, electrically excited, and so on. Yeah, here we see some of the test back-to-back rig. Also, I can mention that we are involved in 2 projects, PowerRise and HEMI. PowerRise is an EU project. Some of you, our partners, are here. And in this project, we look into the possibility to increase the system voltage. I was talking about the charging. It's too low voltages, too low power levels. So if you could increase the power, the voltage level, you could increase the power as well. And in these specific projects, we want to build prototypes at 1200 volts. So you could do that by 2-level inverters using, for example, 1700 MOSFETs, or you could have 3-level or maybe multi-level inverters. So the ambition for this project is to build inverter, hopefully multi-level inverter, suitable for 1200 volts, and see how that will affect the whole system level. It could affect the electric machine winding and so on. So we have a lot of, these are some of the research activities based on the inverter development. And then I would like to finish off by mentioning our DC-DC converter, which I presented at SCAPE conference a couple of years ago, but it's worth mentioning. This is also from Emotion. The first generation have silicon IGBTs. So by changing the silicon IGBTs to silicon carbide MOSFETs, Emotion were able to, I'll make a commercial for you guys now. Reduce the volume by 70%, the weight by 50%, and the increased efficiency by 6% units. It's the same power level, but still you manage to reduce everything like that. And that's by increasing the switching frequency. So in summary, we have silicon IGBTs in our current products, but we are clearly moving towards silicon carbide MOSFETs in our inverters and DC-DC converters. And I think we will continue moving in that direction in the future as well. So thank you. 18 minutes and a half.
Thank you very much, and thank you for keeping the time. Okay, 1 question? Maybe 2.
Since you were showing, thanks for the nice presentation. Since you were showing different groups that you're working with, one of the things that I wonder about is how much automated tests on a software level helps you with, or do you utilize any of them?
I mean, when it comes to software, for example, for the inverter, my colleague here is working with that. It's rather new, so we don't have so much automation yet. So it's hands-on. We do testing, and then so we're not at that stage yet. I would say it's an early stage.
Okay, no more questions.
It works.
Okay, then.
I've seen that in your some type of advanced engineering job that you have done. You have used the discrete component.
Yeah.
In the future, are you going to use the discrete, or are you going to switch?
Yeah, it's not decided. I mean, for the inverter that we have there, we have power modules, for example. But in the generation after that, you never know. It might. We're investigating different types of devices, I would say. So we're not limited. We have dual sourcing in that one as well. So it's different power modules. But in the future, next generation, it might be discrete. So, but it maybe tends towards power modules. I don't know. How about you guys? You at Volvo, you're towards...
Switch to the power module.
We can discuss it.
Do you see that when the Tesla introduced these discrete solutions?
Yeah.
I can say that we have done similar investigation and we have reached to the very good solutions also with the discrete, but at the end when we have done a little business analysis, then we have seen that switching to this solution with the power module is a little more better from cost perspective, not from the performance perspective.
Interesting. Yeah.
Okay. Thank you very much.
Okay. Thank you.
So then we go to the final presentation of this session. It's from Kraft PowerCon from Kenneth Svensson. The title is High Power DC-DC Converter for Fuel Cell Applications.
Yes, good morning everyone. My name is Kenneth Svensson. I work at Kraft PowerCon. I'm an end user of silicon carbide, so I will present the ongoing development project we have for a high power DC-DC converter. The company Kraft PowerCon, we are a global company. We are about 500 employees all over the world. We have 4 R&D centers and we have production in Sweden, India and China. We are working with power conversion from few hundred volt up to several tenths of kilovolt and a few amps up to several tenths of kiloamps. So this project is a new area for us. It's a marine fuel cell system. It's where you put fuel cells in the boat to supply the power. You have this is how the system could look in a boat. In the bottom you have the fuel cells, several of them. The fuel cell acts as a battery with high impedance. It also have high impedance to ground, despite from ordinary batteries. So thanks to that, we need a DC-DC converter to give the same voltage from all the fuel cells before putting onto this local DC bus. There could also be ordinary batteries on the bus to handle dynamic changes and to start up the system before it's running. So we need a DC-DC converter before every fuel cell, before they are put to the DC bus. And because of the impedance to ground in every fuel cell, that is not negligible, it's very beneficial to have galvanic isolation in the converter. For the batteries here, it must also be charged, so the power flow must be bidirectional. So we went out to the market and looked what could we find for this application, and we found that there is no galvanic isolated DC-DC converters at this power level on the market. So we decided then, we develop our own. It could also be used for photovoltaic applications, where we have more or less the same requirement as for the fuel cells before feeding a DC bus. And this grid converter could be exchanged to an electrolyzer for green hydrogen production also. So the requirement for this converter looked like 200 kilowatt seems to be suitable for existing fuel cell modules. It should be scalable up to 10 megawatt. It should be possible to put in cabinets for parallel connections. It must be bidirectional, so you can charge the batteries also. It should have high efficiency. It should be compact. And of course, possible to put in parallel. So the requirement looks like this. Primary voltage in the range of 700 to 1300 volt. And secondary nominal voltage, that's a DC bus, around 1000 volt. So we end up at a nominal power of roughly 200 kilowatt. We will have an efficiency higher than 97% for the whole converter. And as I said, galvanic isolation and bidirectional operation should be possible. So we started to look what topology is best to fit these requirements. And we ended up in the DAB topology, the dual active bridge. The dual active bridge, it's quite common in these applications. It's very well known. It consists of two stages that looks exactly the same, where each stage consists of two transistor modules, drivers for the transistors. And in between we have a transformer with commutation inductance that could be inside the transformer or as a separate component, and DC blocking capacitors. And we also need to measure voltage and current on input and the same on the output. And we need a controller. And we decided to use the best commercially available components for the moment to make as good and compact converter as possible. We would like to minimize the inductance in the commutation loop to have as efficient switching as possible, to have as high efficiency as possible. So we started to look on the market, what's available in transistors. And a little bit about the DAB principle first. You can see the DAB as two voltage sources with a square wave, 50% square wave, and an inductance in between. And the power is adjusted by the voltage, one voltage times the other voltage times the switching frequency and this coupling inductance. And the constant, which mostly is the relation, the ratio in the transformer, times sinus for the angle between these two voltages. So by just controlling the angles between these voltages, you control the power flow. So you could have both a positive angle and a negative angle, so you can have power flow in both directions of the inverter. We started to look for transistors, which transistors is best for our needs here. And we ended up in this microchip transistor with this name here. It's a 1700 volt module, nominal 676 amps. It has 3.75 milliohm resistance. And they claim 3 nanohenry as internal inductance, which is really low. It's an improved 62 millimeter package. It's the old 62 millimeter package where they have made a totally new design inside. In order to meet this really low inductance, we thought we cannot use ordinary bus bars. We must have something else. So we designed a PCB for this, a heavy copper PCB with 0.5 millimeter copper, so it's much thicker than ordinary PCBs. And we mounted ceramic decoupling capacitors as close to the transistors as possible. So this is for one transistor module, this is for the other. Here we have DC link capacitor, and here we have DC blocking capacitors. And we actually measured an inductance in the transistor plus the PCB at about slightly below 5 nanohenry, which we think is quite good. We designed a water-cooled heatsink where you can have 2 SiC modules on each side. So this is the cooler, water cooler, This is the PCB. So on the bottom side here are 2 modules, and here are 2 other modules. So we put 1 more PCB onto this one. So it looks like this. Here we have the cooler. We have 2 SiC modules and 2 SiC modules, PCBs, and DC link capacitor. And then we put this together in a steel frame to make a really as compact building as possible. Little bit about gate drivers. As everyone knows, the transistors need to have gate drivers. And we started with plug-and-play gate drivers, intelligent gate drivers with processors on the low voltage side, but we had severe problems with common mode voltages. At lower voltages, up to 500-600 volt, it worked fine, and at lower current, but when we're reaching 1 kilovolt and 600-700 amps, we disturbed the communication processor. We disturbed the electrical interface, so it was impossible to run the inverter. So for continue with our test, we had to design something else ourselves that works. So we ended up in optical fiber communication. So here we have, it's this board here. Here we have small DC-DC converters, 1 for high side, 1 for low side. And we have optical interface, 1 for high side, 1 for low side. And the best driver we could find on the market with lowest impedance we used here. But this is not the final solution. We don't have any overcurrent protection. We don't have any temperature measurement. So this is just more or less prototype for continue the power test. How do we test this bastard? 200 kilowatt is quite a lot of power, so it's not so easy to get, and it's not so easy to get rid of 200 kilowatt in test. So we found out, because we have galvanic isolation in this one, we could connect the output with the input directly and just feed the losses. So we can run 200 kilowatt here in what direction we want, and we just feed the losses. And we said 97%, that's 3% losses and 200 kilowatts. So we only have to feed 6 kilowatt to test 200 kilowatt. So this works really fine in the lab. So this is how how it looks in the lab. This is a test stand we have. Here in between we have the power modules. Here we have the transformer, some temperature measurements, and yeah, some other stuff for measurements in the lab. But the drawback here is we have the same voltage on input and output side, and we must do other tests than with the same voltage on both sides. So then we built a boost buck converter with the same components as we used in the big converter. So it's just a transistor pack module and an inductor. So this is the same power PCB that we have in the large system, and a large choke. So when we run it in this connection, if we flip the top transistor, then we get a buck converter. So we have a lower voltage on this side than on this side. If we turn it on the other way around with the inductance on this side instead and flip the low transistor, then we have a boost converter, so we have a higher voltage on the output side than on the input side. Still only supplying the losses to the system. So this works really well in the lab for testing. About software, when you develop software, it's not fun to test 1000 volt, 500 amps control algorithms. If something goes wrong, you have a real bang. So we developed a desktop converter for software development, where we have scaled the voltage 1 to 10, the current 1 to 100, so the power is scaled 1 to 1000. So from the software point of view, this one works exactly as the big converter. So we can do the software test on the desktop instead. So this is the transformer also scaled, and the commutation inductances and coupling capacitance. So this is one power stage, and this is one power stage. On the bottom side here, we have the same gate drivers as we use in the big system. So it's exactly the same interface for the controller. So this is the control PCB, where we have a CPU card, and this is the electrical interface that we use in the desktop. Here we have the optical interface that we use in the big system. This is some interface to the outside world, field bus, USB for setup, and CAN communication when we have several modules in parallel. Some measurements. We measured a total efficiency of 98%, 98.5%, and that's way higher than our target of 97%. So we are really satisfied with the efficiency we come up to. We have a power density of about 2 kilowatt per liter for this whole inverter, with transformer and everything. Some notes we did. The gate resistance transistor in the data sheets for this module should be at the range of 0.5 ohm. But it's possible to run with that high gate resistance. We must have as low gate resistor as possible, otherwise we get ringing on the gate, which seems to be a little bit what you are used to. You should have higher resistance if you have ringings, but we found the opposite. And as I said, we had severe problems with common mode current in the gate drive circuits. And some curves. This is a gate signal from one transistor. This is for the other transistor. So we are running between -4 and +20 volt. Maybe we should have a slightly lower than 20 volt, but this is not the final design. This is the drain source voltage, and this is the current in the transformer. So if we magnify the switching, here we have turn off at 800 volt, 500 amps. This is the gate voltage. This is the drain source voltage. The switching looks really nice. There is almost no undershoot at all. This is 900 volt, 600 amps, looks almost the same. But here at 1100 volt and 700 amps, now we start to see this oscillation on the gate. And it gets severe the higher the current is. And we also see at the drain source voltage, it's not so smooth any longer. But it's not a shoot through because the other transistor is not turned on. So it seems like it looks like it turns on and off here. We don't have any really explanation for this yet. And we measured the DUDT of the switching of about 50 kilovolt per microsecond, which is about what we could expect from silicon carbide. So conclusion for this. Our conclusion is the silicon modules works really well in practical applications. But the commercial available gate drives, they are not in line with the modules. That's our conclusion so far. Thank you very much. That's my presentation.
Thank you very much. I could allow one question, or we move it to the coffee break. Looks like to the coffee break. Thank you. Okay, welcome back. So we continue with applications. We have 3 more presentations to go. The first one is from Warsaw University of Technology, Rafał Kopacz. And it's entitled Advanced 1.5 kilovolt DC Charging System based on silicon carbide technology. Please.
Okay, thank you. Hello, everyone. My name is Rafał Kopacz, and I'm from Warsaw in Poland. And I'd like to present results from a joint project with Warsaw University and NTNU in Trondheim and the local company Markel on an advanced 1.5 kV DC charging system. So I start with describing the system, the project, and then I'll go through the system architecture, the converter topologies, and then of course I'll talk about the experimental setup and the results, and in the end, of course, some conclusion. So the project is MORSIC, so modularized, reconfigurable, and bidirectional charging infrastructure for electric vehicles with silicon carbide power electronics. So again, as the name suggests, it's an advanced system. So we have a lot of stuff here. So you have a grid connection, energy storage, EVs, of course, and also an inclusion of photovoltaics. Here are the core features of the system. So of course, first and foremost, it's based on silicon carbide technology, because this is, of course, the way to go with e-mobility and especially expedited voltage. And as I mentioned, we have energy storage system, so we can either support the grid or work off-grid, so there's more flexibility here. We also include renewable energy sources in the form of photovoltaics, because we can look at it in a kind of like a DC microgrid. So this is also often included in such systems, so we also have included the photovoltaics here. As I mentioned, we have grid support, of course, from the photovoltaics, from the energy storage, but also in V2G from the EVs. Another important feature is the reconfigurability. So at first, let's imagine a situation where one EV can charge slowly, want to charge slowly, and then only one DC-DC converter would charge it. But then if we demand ultra-fast charging, then we connect several leads in parallel to expedite the power and the speed of charging, ultimately. And this is what makes it scalable for ultra-fast charging when needed. Furthermore, we have expedited voltage to 1.5 kV DC. We can already see the trend to increase the voltage. It's been already done for energy storage, for photovoltaics, and the same as here with this system. Of course, because of the fundamental increase or decrease in conduction losses. And finally, we have a bipolar DC grid. So instead of just 2-wire DC microgrid, we have 3-wire, which gives us also increased efficiency, but we can also achieve improved flexibility here. And we can see, for an example, of course, we have 800 volts vehicles, 400 volt vehicles. So we can imagine a situation where we have certain converters at full voltage 3-wire connection, and the other one at half voltage with 2-wire connection. And this gives us better operating conditions for the converters. So this is a possibility in the system. So let's now talk about in more details about the converter, the topologies. So for grid converter, we have a NPC because we need bidirectional operation. We need to have the possibility to balance these voltages. And so we need a 3-level system, and then we can employ 1200 volt silicon carbide MOSFETs. Okay, moving forward, we have the EV DC-DC converter, so an isolated converter. Here I show just one example of what could be done and what we have in our experimental setup. So this is a system designed for 800 volt charging. And then we have on an input stage, on the station side, we have an NPC system. And on the secondary side, with lower voltage, we have full bridge. And thus we can use only 1200 volt silicon carbide MOSFETs everywhere. But of course, as I showed you just a second before, you can have alternate options. So you can use full bridge. So of course, the options are vast. But this is the one we've built for the experimental system. And here to improve the efficiency, we have also included soft switching via MCT. Next on, we have the battery storage converter. So this is done in a conventional 3-level DC-DC converter to also have the possibility to to connect it via 3 wires and also have the DC-link balancing capability. Because in a situation where we don't have the grid, we have to balance it somehow. So this was also needed. Also here we included interleaved, so we can lower the ripples on the battery side, which is important. And of course, we have introduced a new common-like coupled inductor configuration, which I talk about more a bit later. And then lastly, we have photovoltaic converter. This could also have been done with almost the same topology as before, but since we are working mostly on research, we wanted to do something else to have larger, more vectors to look into. But it's essentially a conventional flying cap topology, also an interleaved system. So of course, when you would think about an actual application for ultra-fast charging, we would talk about hundreds of kilowatts. But the capabilities of our lab are not high enough, and also maybe that would be very expensive as well. So we have done a scaled model, and each converter can have up to 20 kilowatts, depending on the system. But the voltage was tested fully at 1.5 kV. The switching frequency, depending whether it was hard switching or soft switching, was from 60 to 100 kilohertz. And there we use discrete silicon carbide MOSFETs for 100 volts in each system. An important feature of the system is that we have this 3-power submodule, which is foundation of each converter. So we have this submodule with a heatsink. Of course, the transistors are underneath the power board, some drivers with protection, and DC-link cap. And this is used in every converter. And the basis is that we have an ANPC, but with a quick reconfiguration, just the way that you would solder it, you can change it, of course, into another topology quite easily. So we have one hardware for each converter, pretty much unchanged. So here you can see our experimental setup in a rack cabinet, almost full. One converter is missing. I'll talk about it in a second because it's operational. It just hasn't been added to the cabinet yet. So you can see 2 isolated DC-DCs, 1 battery storage DC-DC, and the grid converter down here. So going now one by one for each converter, you can see the isolated one. So you can see one side module, second side module. The magnetics and capacitors for series resonance are here underneath the control board, and it's all housed in rack case. So you can see, as I mentioned, we have soft switching, so resonant characteristics of the waveforms on the right-hand side, and you can see the peak efficiency is almost 99% here. Next on, we have the grid converter in ANPC. So we have each module here, so 1, 2, and 3. It's covered with the control board, with measurements and all of that, and we have the filtering all the way through with some relays. On the right-hand side, you can see the grid currents for certain DC-link voltages, so you can see quite nice sinusoidal waves with low THD, and the efficiency is roughly 97% maximum. Next on, we have the non-isolated DC-DC converter. So again, same modules, coupled inductors, one here, one underneath, and the rest is all similar. So as I mentioned, this is a new configuration, also with the modulation. And this is a comparison with other state-of-the-art options. So essentially what we get is the same efficiency, same ripples, but simpler magnetic design compared to other state-of-the-art options, and also entirely limited common mode voltage noise, which is very important in terms of filter volume. And finally, we have the photovoltaic. As I mentioned, it's not in the cabinet yet, but it's built, it's been tested just recently, but it's been tested at rated power, and it's all good. But you can see here, there's a slight modification for the modules because this part was added as like an add-on to the project just last year. So it wasn't thought about from the start. So that's why we have a little more modification with the flying cap. But essentially, it's almost the same. And as I mentioned, some have been already tested, still in progress, haven't been tested thoroughly, but we have at full power, we see voltage is balanced and so forth. So it's also operational already. We just need some more tweaks to put it inside the cabinet. So of course, since the system is quite advanced and has a lot of options we can delve into, there's a lot of different scenarios we could imagine. Here it's shown, and what I will show also in an experiment just in a second, is a very simple situation where we'd go from the grid to the EVs. But we have so many options here, it's really hard to show even, because you can go to EVs from each of these three, but you can also do it partially from here and here. You can do one or more in parallel. You can support the grid. So as I mentioned, it's a lot of options that we have possible here. So the scenarios are really, there's a really lot of them. I only show this one here. And let us see the results. So down here we see grid converter. So we see the DC link and the current from the grid. And here we see the current of one EV charger and the another one, and this is the power. So this is, we didn't connect actual EVs, but we have emulated the battery behavior via an electronic load in a CCCV. So you can see we turn it on, we get the voltage, then we get the demand from one of the chargers. So we slowly ramp up the current and the power. It goes up, then there's another, and so on. So you can see that's quite well, behaves quite well, and as we would expect. So it's all good in that regard. And the efficiency we got for this two-stage conversion is 96.5 peak. And I would like to do a remark here. Of course, this is a scaled system. So one would say, why such high voltage here? But this is a scaled system again. If you do a 10 times higher power, then the efficiency would be, of course, really nice. So this is something to take notice of. And in conclusion, of course, silicon carbide devices allow us to really develop these new technologies. And especially when we want to go higher with the voltage, which, as I mentioned, is a trend now. We can see it in a lot of different applications and also in EV. So silicon carbide is really important here to have very high performance with that. Of course, the system is quite advanced, so there are quite a few issues you have to think about, the balancing and so on, but it's also been tested and it's also operating as it should be. And further works will, of course, include working with all the scenarios and looking at the energy management algorithm. For example, we can include some fluctuation in energy price and so on. So there's also a bit of possibility here. And also we have, closer to the power electronics topic, we have also developed a few controllers for multi-stage control. So for example, looking at two converters to, for example, maximize the efficiency, and this can be done, for example, by changing the DC voltage variable within the operation. So this is also an option. So at the end, I would like to give acknowledgements for the team in Warsaw, in Trondheim, and then the company in Piaseczno. And that's it. Thank you very much.
Yeah, thank you very much. We have time for 2 questions, maybe. Ansi?
Yeah. Hello. Okay, congratulations to an interesting work. You said that you have many options here when it comes to let us say, study power flows from different units to another.
Yeah.
So now, if you then think that you will have this system with several systems operating at the same time, will it be the line side converter, or will it be the energy storage unit which will control the 2 voltages in the DC link? Or do you have separated tasks for that?
Okay, so I didn't, of course, given the time constraints, I didn't talk about it, but all the converters, of course, controlled via DSP separately in each converter, and then they're connected via CAN to a system that runs all the system. And it gives the orders for each of the converters. This is what controls the whole system, and this is what the energy algorithm is. So the idea is that we assume that most of the time we have grid connection, and the grid converter is responsible for balancing. And only when we are off grid, only then the battery one controls the voltage. So it's either this or that. So we have thought about it, yes. Thank you.
One more question? Doesn't look like that. Okay, thank you very much.
Thank you very much.
So then we move to the second presentation of this second session. It's from Yang Kim from Revotech, and it's entitled PTC System for Electric Car with Silicon Carbide MOSFETs. Please.
Good morning, everyone. I'm Youngjin Kim, the director of R&D at Revotech. Revotech is revolution and technology. It's an honor to speak with you today about our project, which is part of an international collaborative effort. Today, we will explore the innovative application of SiC MOSFET in PTC controller for electronic vehicle, a key development in our global cooperation. You can see the outline of my presentation here. Today, I will cover two main topics. First, I will introduce our company, emphasizing our founding philosophy and our capability in research and development. Second, I will discuss a global collaboration project that my company is involved in, supported by South Korea and in partnership with RISE in Sweden. Revotech is a company that offers comprehensive solution ranging from planning and development to certification service for automotive electronic control system. And Revotech is an opinion design house. We have both a certification laboratory and R&D center to support these services. Our core business areas are first, we provide electronic control system product for vehicles. Second, we develop a heating system for electronic vehicle. Third, we offer certification and testing service for electromagnetic comparability of vehicle electronics. Next, I will introduce my company's business areas and talk about our global collaboration project. Our company specializes in developing controller for electronic vehicle and is recognized as an opinion design house. We have a rich history of working on diverse projects, including air conditioner and human-machine interface system. Currently, we are dedicated to advanced technology for the next generation of electronic vehicle. Our focus areas include vehicle control units and positive temperature coefficient heater and brushless DC motor controller, all of which are crucial components for electronic vehicles. Once again, our primary focus areas are BCU, PTC heater, and BLDC motor controller, key components for electronic vehicles. The BCU has been developed as part of a national initiative to support small-scale developers who are interested in creating ultra-small electronic vehicles in line with the mission of the opinion design house. This initiative to not only aim to integrate opinion device into our customer product, but also to leverage them in our own product development. Additionally, we are committed to advancing high voltage heating system with a specific focus on commercializing power controller that utilize SiC semiconductor. Our company also operates on EMC lab and has been designed as the external EMC certification center for Hyundai and Kia, focusing specifically on the crucial EMC aspect of vehicle controller. As mentioned earlier, we have a rich history of developing in vehicle controllers. Consequently, we are fully equipped to develop production from the initial design stage all the way through to mass production, tailored to meet a customer requirement. Next, I will discuss about global cooperation project. When choosing an electronic vehicle, the most important factor to consider after cost are the range and charging time. The range indicated how far an EV can travel on a single charge, while advancement like increasing the battery voltage from 400 volt to 800 volt can significantly reduce charging time, enabling a quick boost of about 100 kilometers in just 5 minutes of charging. However, factors like vehicle weight, aerodynamics, and external conditions also impact the overall driving range. It's well known that both gasoline and electronic vehicles tend to have reduced range in the winter, but electronic vehicles are especially affected. This decrease in range is mainly due to the additional energy needed to heat the vehicle interior during cold weather. As vehicles shift from internal combustion engine to electronics one, traditional heating method using engine heat are replaced by electronic heating system like PTC heater. However, these heaters can be noticeably loud in electronic vehicle due to the absence of engine noise, which usually masks other sound. So the noise from PTC heater in electronic vehicle is caused by several factors. First, PWM signal noise arises from the pulse width modulation signal controlling the heater power. Second, ceramic gap noise is generated by gaps between the ceramic grain in the PTC element. So third, vibration. These gaps also cause vibration that are amplified by the heat load, increasing the noise. To address the issue discussed, we propose two solutions. Firstly, develop a higher voltage PTC heater to reduce power consumption from the DC-DC converter, improving efficiency and driving range. Secondly, increase the PTC heater operating frequency to above human audible levels to reduce noise emissions. Implementing these solutions will require replacing the current IGBT with a SRC MOSFET in the controller. This project, backed by South Korea Ministry of Trade, Industry, and Energy, involved a global collaboration with RISE with Sweden. Here's an overview of each participant purpose. RISE is developing a 1200 volt SRC MOSFET. Labotech is creating a PTC heater controller using SRC MOSFET technology. CATEC is ensuring the reliability of these innovations through performance verification. Seongkyungwan University is at the forefront of developing EMC silver paste. Uri Industry is working on high voltage PTC development. This diagram depicts the PTC system, which isn't a half bridge setup. Instead, it generates heat by running current through a register known as the load. SRC MOSFET handles the current flow during switching. In the case of the PTC controller prepared for this test, different elements were used in each of the 4 zones. The IGBT was used in Zone 2, Zone 4, our SRC MOSFET in Zone 1, Zone 3. So we made adjustment to the test environment. We reconfigured the circuit to monitor the current in the element source signal. After modifying the data monitoring position, we checked for inrush. Additionally, we assessed the inrush of both IGBT and SRC MOSFET while varying the frequency. As seen, tests were conducted for each frequency range. This video is an actual operating of PTC heater. We used a thermal imaging camera. It's noticeable that SRC MOSFET has a shorter turn-on, turn-off time compared to IGBTs. This shorter turn-on, turn-off time of the SRC MOSFET leads to higher efficiency. The time it takes for the PTC load to reach 100 degrees is shorter when using SRC MOSFET. Specifically, the SRC MOSFET reached 100 degree 10.66% faster than the IGBT. Furthermore, it's worse. Nothing that IGBT malfunction occurred at frequency higher than 11 kHz. Next. Two major noise tests were conducted under specific conditions. The distance between PTC heater and the microphone was set at 50 centimeters. Measurements were taken with all 4 channels operating simultaneously. Noise was measured for each frequency range separate. We, for noise test or zone, used SRC MOSFET. These conditions ensure accurate assessment and comparison of noise levels across different frequency range. When the PTC heater is in operation, sound is detected across all frequency. However, at 100 kHz, the noise level surpasses the audible frequency range, making it inaudible to human ears. In contrast, the IGBT doesn't operate reliably even at 10 kHz, whereas the SiC MOSFET function normally even at 100 kHz. This indicated the superior high frequency performance of the SiC MOSFET compared to the IGBT. Shall we listen to it? Shall we listen to it? Okay. 15 Hz. Hz. Real sound. 1 kHz. This is 10 kHz. This is 100 kHz. Similarly, white noise. So you cannot hear the sound at the 100 kHz, right? Okay. In this global international collaboration, we successfully developed a PTC controller utilizing SiC MOSFET. With the integration of SiC MOSFETs, we have created an efficient PTC heater capable of operating at high voltage and high current. Furthermore, when employing SiC MOSFETs in the PTC system, we observed normal operation even at an operating frequency of 100 kHz. Additionally, we confirmed a decrease in noise levels above 20 kHz, showcasing the effectiveness of SiC MOSFETs in enhancing performance and reducing noise in high-frequency operations. So, integrating SiC MOSFET into vehicle electronic compressor controllers expand application areas and drive commercialization of our consortium SiC MOSFET. That's all I have prepared for you today. Thank you for your attention.
Yeah, thank you very much. We skip the questions here. The presenter kindly asks you if you have questions, then catch him in the coffee break or the lunch break.
Okay.
Thank you. So we move to the next presentation. It's from Claes Håkan Eklund from Comheat. And he will talk about something very unusual for a silicon carbide conference or Wide-Bandgap conference. New silicon-based power devices will compete with silicon carbide in GaN.
Okay.
Please go ahead.
Yeah, I will, yeah. Yes, we are talking about working on new silicon-based, actual an LDMOS device based on bulk silicon. And we have got up to breakdown voltage from 60 to 150 volt. And this is based on a concept, so it's actually not a conventional LDMOS. We have added a lot of features for improved performance. And we think that later on, show that this performance is about the same as for gallium nitride and silicon carbide, and much better than state-of-the-art vertical silicon devices. And we have simulated the product specification and spikes model at different voltages. Some of the highlights we have done, we have again extended the voltage from 900 volt up to 1250 volt. And it's now stated as from 60 to 112. Yeah. And in addition to that, the die size has been reduced with a factor of 2. And this will more than double the number of good dies out from the wafer. Die cost reduced by more than a factor of 2. Output capacitance has also been reduced by around 30% and will reduce switching losses. No external Schottky is required, which will further reduce cost and also save area. If you have an internal cost, Schottky conventionally, it will nearly double the area. Here we are comparing our LDMOS device with silicon carbide and gallium nitride. And you can see on what is it? Get the pointer to work. See. No? It's not working, the pointer. Okay. Anyway, on the first, you can see this. We make it from 650 volt up to 1200 volt. And what you can see, it's about the same as GaN and COM-heat. Yeah. And this is the silicon LDMOS. As you can see, the silicon LDMOS is much lower. So we have for the lateral device is much higher. And we go to 900 volt, you see the same. Or even if we go to 1200 volt, then we are about par with silicon carbide. So an interesting question could be here that it seems that we are having a lateral device which is much better than a vertical device. Let's assume that we could do a lateral device on silicon carbide. Where could we be? Could we be higher? Probably. It will be an interesting project to really work on. What we have done, Aaron times area, I'll just show that we are getting a factor of 2 improvement. And we are comparing with silicon carbide and GaN, and we are about in the same region. I think, and this is very also dependent. Here I think we have probably more improvements from that we can include the Schottky diode without any area, because then other people have to add nearly a factor of 2 in area. What's more is QRR. Here we are compared with COM-heat without external diode, or with a CoolMOS and a CoolMOS another without. Yeah. And what you can see here that we are getting with external fast diode, we are getting around TRR 50 nanoseconds, which means that it's very fast. Yeah. From this comparison, it's obvious that can give a similar lower QRR without a fast diode, in parallel with the drain and body. This means that lower cost, higher performance, an external diode, that's area and capacitance. This concept is independent on the voltage class. Here are some on electrical parameters, and what is red here is the Miller capacitance, extremely low, and even gate capacitance. And this means that we can use a very low threshold voltage for the MOS transistor, 1.5 volt. You don't need, we can use on other conventional too, but I think the CRR-SSS is low. It's very beneficial for that will improve reducing the effect of spikes on the output. So I think this is a very important parameter. And now very often you make a divide with CISS divided with CRSS, this could be very high value. So I think this is very low, and this probably explains why this switching very hard, fast too. We have a discussion with the top 5 fab house, and the first time we did show this, they said, "We're back, we are not interested." A couple of weeks later, they called back and said, "This is exactly what we wanted to have." So they did change and thought it was very, yeah. And then we have been working a lot together on the process flow, and then have been working on the cost. And they came back and said that this is very cheap compared to this to silicon carbide. And there we are about, and now we are together trying to get a partner, more or less finding a system house which need the products using the technology. So that's where we are today. Okay, that was for, yeah, and what we are going now, we are working on to making this new concept realized on silicon. Thank you.
Thanks a lot, Klaus. We have a lot of time for questions, looks like. Okay. Yeah, we start here.
Regarding the efficiency curve that you have shown at the beginning, you have shown that in the lower voltage that you have a efficiency drop suddenly. What is the reason? What phenomena is behind?
Pardon?
What phenomena are behind that one, that the efficiency drops such a fast in 650 volt?
I don't really understand your question. It's, yeah.
The slide you have shown, maybe I couldn't understand that one correctly. You have shown one slide for the efficiency. This one.
Yeah.
And you have shown that the LD mouse drops in the 650 volt when you use the 250 volt as an input device. What phenomena we have that we cannot compare that one with the, for example, other component like GaN or, for example, silicon? Why we have such a gap?
We just have a better device. Yeah.
Sorry, what?
We just have a better device, our new LDMOS device. We have many new features.
You're talking about the blue curve, the silicon LDMOS.
It's the red dot.
But this is not the COM-heat device. The COM-heat device is the red dots, and which is at the same level at the GaN devices.
Okay. 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 Yeah. Okay.
Okay.
No.
Francis, you had a question? No.
Can you describe qualitatively how different structurally the new devices compared to the existing silicon LDMOS? Double field plated or?
We have changed some of the key process steps. Yeah.
Okay, so structurally it looks different.
The structure you can say the same, but we have done some changes. Yeah, some key changes.
Field plating.
Pardon?
Field plating.
Yeah.
Yeah. 2 field plate?
No.
Oh, 1.
Just 1 field plate, yes. No. Yeah. There are other features, yeah.
Yeah, thank you for your nice presentation. Okay. My question is, have you done any hard switched? Because I can still see you have got a high QRR. Did you hear my question?
No.
I can still see on your CAM LDMOS, you still have got a large QRR. Have you done any hard switching? applications to compare against GaN? Because this is where the GaN outperform the silicon devices.
No, we haven't done it.
Right. But can you explain, you still have got a high QRR?
Yes.
So it will not be suitable for hard-switched application then, right?
No, but was it that hard though?
Yeah, because in the hard-switched application...
It was lower than competitors.
And not on the QRR.
Yes. So I can't get it yet.
Okay.
Okay, we can take it later, yeah. I'm pretty sure it was lower.
Okay, maybe you can take it in the in lunch break or something like that. Okay. The guys in the back tell me that I should stop it. Okay. Now we leave applications, yes. We go to market and roadmap. And there we have a presentation from Elena Barbarini from the old group on GaN and silicon carbide power device technology and market overview. Please.
Thank you. So hello everybody. I'm Elena from YOL Group. So actually our presentation will be done in two parts. I invite my colleagues. So it will be split in two parts. First part will be on the technical status of the art of silicon carbide and gallium nitride devices, and the second part I will present to the market status. So just for information, so YOL Group, we are a French company, and actually we are three main activities. We do market analysis on semiconductor fields, technology, cost manufacturing analysis, and characterization of device, in particular silicon carbide MOSFET. So the first part will be technology analysis, split the silicon carbide and gallium nitride, and made by my colleague Amin. And the second part will be the market analysis, again split with the silicon carbide and gallium nitride, and then there will be the conclusion. So I'll let the microphone to Amin.
Yes, thank you, Elena. I'll speak in the mic. Hope it will sound well. For technology trends, I'll start by silicon carbide power devices. So here we have the roadmap of the different generations and technologies of SiC. From 2011 up to 2024, for 2024, and I think, it's on the second line, just a typo. So we see the historical players from RAM, Wolfspeed, ST, Infineon, that also continuing to offer the more recent technologies up to the recent years, but more and more we see acceleration of the introduction of the recent platforms, especially from Asian players. And we see some Chinese players here, InventShape, GoFort, that are really introduced in the recent years. So I would say acceleration from the last 5 to 6 years. We have observing that with new voltage classes, more and more power modules, also targeting automotive applications. So these players, of course, are adopting two different technology designs concerning their gate designs. So as we all know, we have planar gate technology and trench gate technology. The majority of players are adopting planar gate technology, mainly because of the less complex manufacturing process. And a few of the players also adopt trench gate technology, but some players are also announcing for the future and next generations to adopt trench. So mainly for different advantages, such as the reduction of the die size with such technology. So here I'm taking two examples of such the two designs. So the first one from Wolfspeed, planar gate design, and RAM as trench gate technology, the evolution of the different generations from generation 1 to 3 for Wolfspeed, generation 2 and 4, so to planar second generation up to fourth most recent generation from RAM Semiconductor. And there we see clearly two paths, okay, two designs, but one target. Here I'm focusing on the performance, of course, by evaluating the figure of merit, gate charge times on resistance, which is improved for both designs. And also we see improvement of current density, also partly thanks to the reduction of the pitch all over the different generations for both players. Still talking about performance, and I want to highlight here for the first time at your group, we are testing really different competitors of silicon carbide devices in our new product concerning performance analysis of silicon carbide MOSFET. We have the same test bench in the similar test conditions, which is quite different and easier than just comparing from data sheet from different players with not exactly same test conditions. And here I'm giving an example from the report where I'm presenting the leakage gauge current for different competitors from A to E, and linking them to the physical analysis, physical parameters we are measuring through the tear down as gate oxide thickness here as an example. Yesterday we had great insight from presentation concerning the gate oxide reliability and impact on the device performance. And here we are really testing and showing this correlation. Of course, here we see that some players employing thicker gate oxide succeeding to reduce this leakage impact of the gate current. So now moving to gallium nitride power device, I will give some insights. So the picture of gallium nitride is slightly different. It's more, it's wider, I would say, more various solution coexisting. So from substrate, we have different types, silicon, sapphire, and more new substrates. For now, we have all observing as well, like QST. Different mode of functioning, D mode, E mode. We had discussions in the presentation yesterday about this as well. And also wide range of device voltage from 40 volt up to 1200 volt. Also packaging, we are talking about discrete or more integrated solutions like SiP or SoC as well. But at the end, the solution is really device related regarding the requirements and also the application needs for the end users and the application itself. But in all cases, the standards are there as well for gallium nitride, for the according to the JDEC or automotive qualification as well. We have them, and all depends on the requirements and the application. So here I'll focus about some examples of this diversity. Concerning the substrates, the majority of companies, of course, as you all know, are adopting the silicon substrates. Others, like Transform, Power Integration, work on sapphire, allowing some less complex, I would say, buffer layers for the GaN epitaxy. And what's new, and we are expecting like new substrate for gallium nitride as well, more and more. And an example from Chromis here, the QST substrate, which is engineered substrate that is more thermally matched and allows to go to higher voltage classes, and also an easier monolithic integration, especially regarding the buried oxides in the engineered layers of the substrate. So another aspect is the packaging, various types of packaging, from traditional TO to now more leadless packaging for less, more optimized parasitic aspect, and SMD regarding the consumer application of the gallium nitride, embedded dies from Infineon GaN system, and wafer level packaging, which is more for low voltage application. So what's next for gallium nitride? Indeed, if you expect to go to higher power, so 50 kW, 100 kW and more, we need power modules. And indeed, we are seeing some collaboration, some projects between gallium nitride device players with some module makers. And here I'm showing two examples with GaN system, Infineon GaN system with Silver Micro, for example. Here it's an example of a traction inverter gallium nitride module, 75 kilowatt. and also another example with a startup QPT, which is based in UK, which have projects also with Infineon GaN system for the QGAN module. So that's all for technology, and now I let Elena present some market aspect.
Thank you. Okay, so now we move to market trends. Again, the split will be the same: silicon carbide first, gallium nitride, and then conclusion. So I will start with the big view. So about what we expect in global for the silicon carbide and gallium nitride device in the power market by the end of the decades. So actually here it's what we expect, and then my idea is to explain how we get this conclusion. So now in 2023 the market will be about of GaN and SiC in the power device will be around 13%, and actually we expect that will reach at least 20%. By 2028 at the end of the decades, and so the main application I will present in detail later will be actually fast charger data centers for gallium nitride and electric vehicles and renewable for silicon carbide. So how we get that? So let's focus with silicon carbide. So just a bit of history. So the booming and entering of the market as a finalized product of silicon carbide was mainly in 2013. And at that point, the market value 100 millions, and the application were mainly photovoltaics, industrial power supply. We were not talking about too much about automotive. And the main player were Cree. In the past was in Cree, Infineon, ST, and ROHM entering the market. Then 2017. The introduction by Tesla and ST, the first silicon carbide device in an inverter, okay, physical device. And here there was much more interested actually for integration and for the automotive. So actually, yes, automotive. Okay, we discussed all these 2 days about battery electric vehicles. So the requirements are obviously long range, minimize battery costs. If you are going to electric vehicles, decrease the space of the inverter to increase the space of the battery. So smaller size also of silicon carbide device, reliability obviously, and increasing the power, also thermal dissipation. So these are actually, there are some drivers for SiC in SiC. Silicon carbide is in this case. And so actually what we have seen in the past until now, it's mainly the 400-volt segment, but we really think that actually the driver of the market will be the 800 segment battery electric vehicles for silicon carbide. And so actually the more and more players are, but as you see in these 2 days, entering this segment. So now who is leading in the power device? So here's the list actually of the main leaders in global power market. So you have by the latest 3 years, the evolution. And as you see here, actually all the players are investigating, at least investigating R&D silicon carbide devices. And in terms of supply chain, actually we have 2 types of supply chain. There are some players like Infineon, Onsemi, ST that actually are integrating all the supply chain and try to have in-house also the wafer substrate and epitaxy, and other players like Mitsubishi, ROHM, Bosch, Mitsubishi, Bosch, that they prefer actually to externalize the substrate. So actually there is a booming, or actually much more interest for founders that are entering the market, especially in China, and they provide the substrate. So we think that this is actually a business opportunity for founders and the substrate makers. And then if we look about the power SiC device revenues, so focusing on the SiC revenues in the power market, here you see the evolution actually of the latest 3 years. I have to start saying that actually there was a bit not deceleration, but stabilization of the market of silicon carbide in the latest year after the booming of 2017, 2018. And so here you see that actually the leader now are still ST, Wolfspeed, Infineon, and Rome, and it's quite interesting actually the increase of onsemi in the last years, thanks to their strategy and the collaboration with automotive players. So what we see also in the SiC ecosystem, it's has again something that we will see maybe in the next presentation, more and more development for the packaging, because we have presented the technology, planar trench. Now we need to improve the packaging, and the second point is the move to 8-inch. So obviously to decrease the cost of silicon carbide. And so actually in the coming year, we will expect an increase of the facility, or at least an investment in 8-inch silicon carbide facilities to reply to the demand. So currently there is just Wolfspeed that has a production phase in 2023 for 8-inch wafers, but actually here you see all the main players all around the globe are investing or announced to invest in the development 8-inch. But maybe we should go to overcapacity. So, and actually what we expect, if there is a massive increase investment in 8-inch wafer, and until now the electric demand for electric vehicle demand was a bit slowing down with respect to the last year. Actually, what we expect that probably will be over capacity of power SiC wafers. So could be see from actually in a positive point of view, there will be maybe more confidence in silicon carbide technology. Potentially there will be decreasing of silicon carbide cost, but also new entrants that are arriving and that do not have the potentiality to have a high yield device. Maybe they will see an erosion of the price for this device, maybe with lesser yield. But at the same time, that could be an advantage for the purification in other segment, not automotive, and automotive will still require high quality device. So from that point of view, we don't see a big erosion of price for the automotive qualification device. So we have seen what was in the past. So here's a summary of the market evolution of silicon carbide device and what we expect next. And linked to what I said, actually we have seen, yes, the really booming. So here you have actually our expectation, our hypothesis of the evolution of the silicon carbide market with the year-to-year change. We see really with the entrance of 400-volt segment, where it was a peak. Then a slow stabilization in the last years due to the economic situation, a consolidation in Q1 2024 now, and then why not a ramp up again thanks to the new the movement, actually the introduction of 800-volt vehicles, and then we expect again an increase of silicon carbide market, mainly driven by actually automotive, but also industrial application. So then I moved to GaN power devices, so same history. Gallium nitride, obviously, it's younger than silicon carbides. I mean, in terms also in introduction in the market. So the first device we had, 2015, really, and we finally in the smartphone charger later. But actually, there was and there is a lot of investment in gallium nitride. So in the latest 3 years, once gallium nitride proved the interest for commercial and for consumer applications, so all the charger, and actually that's attracted much more players. They will see the potential of gallium nitride market, so consumer market. So here it's a bit the late history of the latest 3 years in terms of acquisition, investment, and partnership. So you see the supply chain is changing again in the last 3 years. There are the epitaxy business with a new player entering new solution and a lot of collaboration between the epitaxy suppliers. with the fabless and fablight that are already there, they make collaboration with IDM. And actually, what we expect that there will be a bit of increase of IDM. But there are also other players that could be interested and could enter the GaN device market thanks to different reasons. So there are IDMs, established IDMs that they acquire. You see in the last year, so the acquisition. So they acquired the gallium device, the gallium nitride device manufacturer to enter in their business. But we have also players like a bit, let's say, in the past, so players that coming from LED, that actually they have the equipment, so they could re-enter the market of GaN and have interest in to get this part of the market. And then silicon fab, like for example Samsung, that they have the platform on silicon, and so why not to invest in gallium nitride device? They have already the platform, 300 volt, and they can launch also this service. And then there are this is a question we'll see in the future. So the fabless power GaN players, the idea is for now they are there. We see how they could collaborate with the other players in the market. But actually what we expect and what we think will be the trends in the future is that now the situation is main player, fabless and fablight, and we think that we will go more and more to IDMs and also in the GaN industry, like for silicon carbide. So again, the expectation of the gallium device market in the future years, as I say, the main trends. So again, we had a booming with the entrance in the consumer market with the chargers, and then we see the entering in the automotive industry first with onboard charger. Then we will see with the traction inverter. But the idea is that slowly, also the power GaN device market we will increase thanks to mainly these two applications. So conclusion. The history of silicon carbide, gallium nitride. Okay, I respect silicon carbide. Silicon carbide is still there. It's a mature technology. Silicon carbide and gallium nitride are still in growing phase. What we think are really the challenges. So for silicon carbide, the expansion, the capacity expansion, the moving to 8-inch, the cost. And for gallium nitride, mainly the moving to 1,200 volt device and their ability to reply to the automotive requirements and power module integration. But what it's happening now is actually there are a lot of investment. Not only, I entered also silicon because it's still there, so a lot of investment also in silicon carbide. There is a transition through 300 millimeters, the expansion of front end, back end fab, new packaging also in this case, and for silicon carbide and gallium nitride again, we expect 20 billion investment for silicon carbide and 4.5 billion investment for gallium nitride in the next years. That's all. Thank you.
Yeah, thank you very much. We can allow a couple of questions.
Year to year,
why don't you keep it?
The year-to-year growth that you have shown for the silicon carbide and also gallium nitride. What is the status of the IGBTs? Is this similar to that one, the same rate, or we have a?
Let's say that the IGBT is quite stable. For there was not so big a fluctuation. There is a slow increase still. IGBT is still there. I think IGBT, but I don't know. I can focus just on IGBT, but there are also MOSFET. In the automotive vehicle, there is still a lot of MOSFET, so the market is still there. There is still interest. The fluctuation is less. It's still growing a bit slowly, maybe year to year. not 62, 57, but more 20, 25. It is still slowly growing because still it's needed the silicon, even if there is silicon carbide and gallium nitride. We will see there are maybe new solution of double integration, silicon carbide plus IGBT in the same modules to balance a bit still the cost of silicon carbide.
Is this, have you seen you know that last year Tesla said that they are going to use both silicon carbide and IGBTs.
Yeah.
Have you seen the effect of that one on this market?
Not too much. I mean, we've seen again the silicon is still growing slowly, but again was not the booming when Tesla made the announcement. Or the opposite, that when Tesla entered the silicon carbide was the booming.
Yes. Thank you. Thank you.
There's a question, yes.
Thanks for the great presentation. You showed the first unicorn gallium nitride company. Would you identify them as the same type of, I mean, the question is the type of investment that goes into this. Is this based on the profits of the company, or is it based on the growth?
The profit.
So they are already, like, if we look at that,
Yeah.
Navitas, is that already profitable?
So I cannot reply to this question if they are really profitable, but the booming of the investment and actually the booming of the interest of consumer, they really expect a growing profitability quite fast.
Thank you.
Are there more questions?
For low voltage, I mean, I'm not talking about 1,200 watts.
Doesn't seem to be the case. So we close the session and can go to lunch. Let's thank all.
Thank you.